Section 5.2, Basic Rules of Probability. In Section 5.1, we looked at the very basics of probability, just doing an F over N type of probability. How many ways can the event occur divided by how many things are possible. In this section, we're going to start looking at some new definitions that can combine events, and we're going to start out by looking at the AND event and the OR event. And as we do that, I'm going to define these using the Venn diagram over here. And just as a way of kind of thinking about it, I'm going to think about this sample space box in the Venn diagram as being like a dartboard, and then my event will be kind of where the dart lands. So just kind of keep that in mind as we go through, and I'll use that as I discuss these examples. So for the event A and B, we define that to be the event that both A and B occur. And I'll fill in that blank over here in just a second. Let's think about it here. Where would I have to land so that I could say both A and B occurred? So think of it as a game where I'm going to throw my dart. It's going to land somewhere in the box, and then randomly they're going to light up these two circles, and I win a prize if both A and B have occurred. So if you think about that, I can't land over here because that's just A. I can't land over here, that's just B. I definitely can't land in the corner because I've missed both. So if I want to win the prize, and that means that both A and B have to occur, I need to land in this overlapping spot, because if I land in here, then I'm in circle A and I'm also in circle B. So that's the official definition of an AND, that both A and B occur. But what I think is a good thing for you to remember is that AND is the overlap of the events. So when you think about an AND, you want to think about this Venn diagram picture, and you want to remember the word overlap. Alright, the other one that we want to look at here is the OR. And for A or B to occur, that is the event that either A happens, or B happens, or both happens. So this time we're playing the same game. We're going to throw our dart. It's going to land somewhere in here, and then they're going to light up the two circles. And the rule of this game is we win the prize if A or B or both occur. So what if I land here? Would I win a prize? And the answer is yes, because A happened. What if I land over here? Would I win a prize? Yes, because B happened. The tricky part is, what if I land in the middle? There's a lot of people who think that when you say OR, it's one or the other, but not both. But if you look at the definition, both is included. So if I land in the middle, that would definitely be a prize too. So when I'm thinking about this for calculating probability, the way I think of it is anywhere in A would be fine, and then anything in B would be fine, but I don't want to double count this overlap part, so when I shade it, I shade all of A, and then I just shade the part of B that I haven't shaded yet. But the overlap is shaded. I just don't shade it twice when I go through and do that. And if you want to put that into different words, it would be for A and B to occur, at least one of the events must occur. So you don't need both of them. It doesn't have to be just one. It could be at least one. So if it's just A, fine. If it's just B, fine. If it's A and B that overlap, that still satisfies the OR, because at least one of them happened. Anything one or more occurring would satisfy that. And when you're thinking about the shading, I think that's important for working out OR problems when you're doing homework and test questions. So when you do that, think of, you want to count all of the first and whatever's new from the second. So I'm going to write that here too. All of the first plus whatever is new from the second. And if you use that rule, I think you'll find that an OR is not such a tricky thing to do as we move along. Alright, we're going to go ahead and practice that with an example. And the example I'm going to use, kind of a common one to be used in a statistics class, would be drawing a card from a standard deck of 52 cards. So the tricky thing about using this example is some people play cards all the time. They're very familiar with it, like me and my poker habit. But some people don't play cards at all, and they don't know the deck at all. So if you look in section 5.1 or 5.2, there is a picture of the deck that tells you what you need to know. I'm going to kind of tell you what you need to know as we go through this problem, and I don't ask card knowledge questions on tests, so you don't have to worry about having to memorize all these facts for a test. But I do think they make interesting examples. So sometimes when you're working with probability, you do want to go ahead and define some events in terms of words. And so they've done that here, defined 4 events, A, B, C, and D. A is the event the card is the jack of spades. C is that the card is a jack. C is that the card is a spade, and D is the card is a face card. If you play cards, you're probably familiar with all those ideas. If not, I'll be explaining them as we work through this problem. So looking at question A, find the probability of C and D. In question B, you find the probability of C or D. I would say the most common mistake that people make here is getting mixed up between the and the or. So I would recommend that you just pause this real quick and try and answer these two questions. And as you answer them, make sure you look back up at the Venn diagrams and think about the way we shaded them in the counting, and then go ahead and resume the play and see if your answers matched. Alright, so let me go ahead and do the probability of C and D. So first of all, when I do a probability that is in any way tricky at all, I'm going to start with the denominator. And the denominator is based on how many things are possible. So what we're doing is selecting one card at random from a deck of 52. So we could get any of those 52 cards. So our denominator is going to be 52. And then I work up to the numerator and I say, okay, out of those 52 cards, how many of them are C and D? How many meet both descriptions? They're spades and they're also face cards. And it turns out that there's 3 of them. And I'll go ahead and list them, let's see, down here. There's the king of spades, that's both a face card and a spade. There's the queen of spades, that's both a face card and a spade. And there's a jack of spades, which is both a face card and a spade. You would not count something like the jack of hearts, because even though that's a face card, it's not a spade. You wouldn't count a card like the 8 of spades, because even though it's a spade, it's not a face card. When we see and, you need things that are in overlap or that have both traits, and these are the only 3 cards that have both. And so just a reminder here, the face card is a king, a queen, or a jack. Some people learn that aces are face cards, but I'm going to tell you that is not correct. It's a king, a queen, and a jack are the face cards in a deck. So 3 out of 52 is our probability. I'll come back with the calculator in a minute and I'll change that to a decimal, but there's all of our work and the logic of it. So now let's go ahead and look at the OR question. Again, we're selecting one card out of 52, so the denominator on this question is going to be 52. And with an OR, it's different. The card doesn't have to be one or the other. It doesn't have to be both. It could be one or the other or both. But really, when I do an OR, I want to think about this picture up here. Count all of the first one and only the new stuff from the second one. So let's go back down here and look at this and say, okay, first then I want to count everything that is in event C. And C is the card is a spade. Spade is a suit. There's 4 suits and they're divided evenly. So 52 divided by 4 is 13. There's 13 of each suit, including spades. And according to this Venn diagram up here, I want to count all of the first one. So I want to count all 13 spades. And then it says plus anything that's new from the second. So this is where you just want to be a little bit careful. Some people will go to the face cards and say, okay, that's the part D. That's a king, a queen, or a jack. So there's 3 of those. And then there's 3 of those in hearts, 3 of those in diamonds, 3 of those in spades, 3 of those in clubs. And they will come up with 12. But if you do that, you're counting the king, queen, and jack of spades right here, which we do want to count, but we already got them right here. So of those 12 face cards that are left, we want to count only the ones we don't have yet. So we would want to remove the 3 right here that have already been counted in this 13 and not count them again. And then we could simplify that. Let's see, 13 plus 12 is 25 minus the 3, so that's 22 out of 52. You could go ahead and reduce that, but there's really no point because we're going to go to a decimal anyways on that. So let me go ahead and grab the calculator and we'll finish that off. So let's go ahead and take a look at that. First one was 3 out of 52. So we're going to round that to 4 decimal places and say that's 0.05, and then let's see, it's a 7.6 but followed by a 9, so 7.7. And then for the OR we had 22 out of 52, and that's going to be 0.423, and then there's a 0 but followed by a 7, so I'd round that up and make it a 1. So there's a couple things to watch out for when you're doing these and ORs. One of them you may have seen as you pause the video and tried it yourself. Sometimes people mix these up. So they'll do the 22 up here and the 3 down here. So you do want to remember that the and requires only the overlap, so it shrinks things down. The or is all of one plus the other, so it's going to grow to a bigger. So you do expect the or answer to be bigger than the and answer. And then the other mistake that is fairly common with these is to double count. And you may have found that you made that mistake when you tried it to all 13 of the spades plus all 12 face cards would be a 25. A very common wrong answer. But we only want to count the new stuff from the face cards, so not those 3 spades we already have in the 13 cards here. Sometimes I tell people, imagine that you took the spades and you dealt them all out over here, and then you looked at your deck and said how many face cards in it and what's left. You would only find 9, because even though there's normally 12, 3 of them are sitting in your pile over here from when you counted the spades. So the tricky thing about doing an OR problem is to be careful not to double count the overlap of the events. And that's what would happen if you counted these 3 cards here and again over there. And that is a very common mistake, so watch out for that when you're doing homework or test questions. Continuing on in section 5.2, we're going to look at more examples of an and an or. This time I'm going to show it to you in a contingency table, which is a table that contains 2 variables at the same time. We have the type of vehicle, which is our V variable. It could be a car or a truck, and we're going to look at the age of the vehicle. It could be newer, older, or kind of in the middle, and that's our A variable. And they're both contained in one table. So let's go ahead and read through the problem, and I'll continue to kind of explain how the table works as we go through the example. So the number of cars and trucks in use by age are as shown in the following contingency table, and the frequencies are in millions. Just a quick pause there. When they say that there is 27.8, that's actually 27.8 million, so we should keep that in mind as we do the problem. Suppose a vehicle is selected at random. Write each of the listed events using probability notation and then find the probability of that event. So event A is that the vehicle selected is a truck. So first I'm just going to do the probability notation. They want the probability that the vehicle selected is a truck. Well, the type of vehicle is our V variable, and a truck is option V2. So I'm going to say they want the probability of V2 right there. And then when you go to do your probability, you want to start out with a fraction and then change it to a decimal afterwards. And when I do this, I'm going to think about the denominator first and say, well, what is it that I'm randomly selecting? So suppose that a vehicle is selected at random. When they tell you that, that tells you what your sample space is. It's all vehicles, and that includes both the cars and the truck, regardless of the age. So it contains everything in this chart, and that would be the 193.4, the grand total. So that's typically what you'd start off thinking is going to be your denominator in a probability question involving a contingency table. We'll see some exceptions to that in the next section, but that would be your initial thought, that unless there's something to indicate otherwise, I'll use the grand total. And then out of all 193.4 million vehicles there, how many of them are V2? So we want all the things that are V2 in the whole table. So we go down to the bottom and take the total for that column, which is 70.2, and that would be our probability. So we're choosing out of all the vehicles, and we want to know what's the chance it's a truck, so we count up all the trucks divided by all the vehicles. And I'll go ahead and convert that to a decimal real quick. 70.2 divided by 193.4 gives us approximately 0.36, and it's a 29 but followed by a 7, so I guess I'd change that to a 30. So that's that one. And then let's go ahead and just try another one to get more practice at the table. The vehicle selected is between 6 and 8 years old. So the between 6 and 8 years old would be, let's see, that's 6 through 8. It said inclusive, so we do want to include the 6 and the 8, but the through symbol is inclusive, so that matches up. And I would put the A2 there, and I would use the same strategy. I'd say, well, what are we randomly selecting? A vehicle. So how many of those are there? 193.4. And out of all 193.4 of those vehicles, how many are A2? So I wouldn't just count the cars or the trucks. I would count out of all 193.4 million vehicles. And so when you look at that, the total number of A2 things is 40. And then again, I'd go to the calculator on that. So let's have a look at that. 40 divided by 193.4, we get approximately 0.2068. So those are kind of the basic probability questions. There's no ands or ors yet, just an individual item. And when you're doing just an individual variable, you're going to use the total for that column or row divided by the grand total in the table. Just worth a quick mention, it's not really 40 million, it's not 40 over 193.4. It is 40 million over 193.4 million. So if I want to adjust those units, what I'd need to do is multiply top and bottom by a million. But if I'm going to multiply top and bottom by the same number, that's like multiplying by 1, so it wouldn't actually affect the decimal. So in regression, when we had adjusted units, we had to think about all that all the time when we were making predictions, interpreting slope, and so on. But with probability, because that same adjustment would happen in the numerator and denominator, that adjustment would cancel out. So we don't have to bother adjusting the units even when we are dealing with adjusted units. Alright, let's go ahead and look at how an and an or work in the context of this table. So with question C, they want us to give the probability that the vehicle selected is a truck between 9 and 11 years old. So when I read the truck part, I'm hearing V2 right there. When I hear the between 9 and 11 years old inclusive, that looks like that would be A3. And then the question is, which is this? Is this an and or is it an or question? And we see the word between, so it doesn't really say straightforward whether it's an and or an or. And it's just some of the subtlety of the English language, I suppose. But we're going to have to think about which one this is. If someone tells you, I'm going to buy a truck between 9 and 11 years old, are they saying it's going to have both of those traits or at least one of them? If it's both traits, that's an and. If it's at least one of the traits, that would be an or. So if they bought a brand new truck, did they buy a truck between 9 and 11 years old? I would say no. They didn't satisfy this part. When I read this, it sounds like it's going to be a truck and it's also going to be in this age group. So when I translate that into probability notation, I'm going to do that using the word and. And then I'm going to think about the Venn diagram, and in the Venn diagram, an and is overlap. So I'm going to think, okay, we want V2 and A3. So I'm going to circle those so that it's kind of like the way we had events circled in our Venn diagram on the previous page. And then when I do the probability, I'm going to think about that. Typically with probability, I'm going to start in the denominator, so I'll do that here. We're randomly selecting a vehicle, so we're choosing from all 193.4 million vehicles. And then how many of them are in the and of these two events, which would be equivalent to saying how many are in the overlap of these two events I've circled. And that would just be this square right here being the overlap. So it looks like there's 10.7 things that are both in A3 and in V2, and that would only be the overlapping stuff. And then we can finish that off with the decimal. So 10.7 divided by 193.4, and we get 0.055, and it's a 3 followed by a 2, so I'll just leave that as a 3. And then one more on that, we have the vehicle is selected is a truck. That's still the V2. It's between 9 and 11 years old inclusive. That would still be A3, just like in the last problem. But this time, we see the word or there. So it's going to be the probability of V2 or A3. And when we go to do this one, we have the same denominator, 193.4, but we have a different strategy. When you have an or, you want to count everything from the first one and whatever is new from the second one. Let me go ahead and grab a different color here. So for the V2 part, I want to count all of these squares right here. I don't highlight the total because if I do that I might count this and then count that again. It would be double counting all that stuff. But these are all the different trucks. And then I want anything from A3 I don't have yet. And that would just be this square right here. And one of the things you might want to think about before you go to the calculator is, alright, so how many squares is that? And it's 1, 2, 3, 4, 5 squares total. So we want to add up all the stuff in those 5 squares, whether it was just in A3, just in V2, or even if it was in both. Be careful not to double count the overlapping part. So you want to count 5 squares, not 4 plus 2, but these 4 plus just the new stuff. And when I do that, I could go ahead and just in the calculator do this, plus this, plus this, plus this, plus this. But it's actually a little faster if I take whichever one had more in it, which in this case would be the trucks, and I just use their total, 70.2. So that got all 4 of these squares. and then say what have I not gotten yet, and that would be this 23.3. Once you start using totals, you do want to be careful. Don't use this total and that total because then you're double counting. Use one of the totals and then just count the new squares that haven't been counted yet from the other one. So you could add these together. I'm going to go ahead and just go straight to the calculator and get the decimal on this. Just remember, when you have addition in the numerator, you need parentheses around that to make sure the order of operations happens correctly. So 70.2 plus 23.3 and divided by 193.4. And apparently I messed something up there. Let's see what I do. I forgot the parentheses right there. And I do want you to notice I just immediately knew something went wrong. I'm calculating a probability. Probability should be an answer somewhere between 0 and 1. So when I get a 70, something's gone wrong. I know that for sure. So let me go ahead and try that again. And I guess it looks like I accidentally hit the 9 instead of the parenthesis key. So I'll get the close parenthesis like I was supposed to the first time. And then do that division. Now I get what's a more reasonable answer for a probability, something between 0 and 1. So 0.4834, but the 4 is followed by a 5, so it's going to round up and be a 5 right there. Alright, so that gives you a little bit of a sense of how contingency tables work, and it also, I think, gives you another vision of how the and ors work. And I actually like doing ands and ors on these contingency tables because it feels a lot like the Venn diagram, where we can circle and look at overlaps, or we can shade all of one and just what's new from the second one. So I think these contingency tables are a really good spot for you to try and work on your understanding of the and the or. Alright, let's go ahead and look at another definition. This definition is of mutually exclusive events, and two or more events are mutually exclusive, which we'll abbreviate with an M and an E, if no two of them can occur simultaneously. On the previous page I talked about thinking about probability as throwing a dart into a box and then these circles light up and we think about whether we have won a prize or not. So imagine we had been told that throw your dart, we're going to light up two circles, and as long as your dart lands in both of them you'll win the prize, and then they light up the circles like this. I think we'd feel a little bit cheated because it's not even possible to land in both because there's no overlap, and that's an example of mutually exclusive. Suppose that we felt cheated by that and they said, okay, I know you didn't feel right about that. If you play again, we'll light up 5 circles next time, and as long as you land in 2 of them, doesn't matter what 2, we'll give you a prize. And so you throw your dart and they light up the circles and it looks like this. You're still going to feel cheated because there was no overlap anywhere, so it wasn't possible for you to land in an overlap. And mutually exclusive groups, whether it's 2 things or 5 things, always have that trait where there's no overlap anywhere. So this is a mutually exclusive pair, and this is a mutually exclusive group of 5. I do want to kind of caution you that to be mutually exclusive means there's no overlap anywhere. So if you had something like kind of our Olympic rings sort of picture, there's no overlap between this lower left circle and the upper right circle, but I still wouldn't say this is a mutually exclusive group because there's definitely overlaps happening somewhere. So if there's any overlap anywhere, then it's not mutually exclusive. You need no overlaps at all to say that they are mutually exclusive. And then just one final note about that before we look at examples. If you're dealing with just 2 events, you can express that in a probability way and say, okay, if they're mutually exclusive, that's going to happen if and only if the probability of landing in the overlap is 0. So remember, if a probability is equal to 0, it means that event is impossible, and it is impossible to land in the overlap when there is no overlap. And just a note about this notation, that's not a misspelling there. An IFF is read as if and only if, which means this is a 2-directional statement. Sometimes people say it's a defining statement. So A and B are mutually exclusive implies that the probability will be 0, but you could read it backwards as well and it would still make sense. If the probability of A and B is 0, that implies that those 2 things are mutually exclusive. Okay, continuing on, we're going to look at another presentation of our information and see how that affects calculating probabilities and ands and ors, and also start looking a little bit at the definition of mutually exclusive events in this context as well. So the chart shown below lists the number of absences for each of 63 stat students during the first 22 days of the semester, which just by the way is the number of days that you typically have before the drop date comes along. So this is looking at how many absences people had just before the final day to drop came along. So just reading the table, if you look at this 1, that means that student missed only 1 day. And then how many students were like that? There were 15 students that just missed 1. There were 22 students who hadn't had an absence at all. There were 3 students who had missed 6 days. There was even a student who had missed 7 days. So that's the way you would read the chart. Now consider selecting a student at random and each of the events listed below, and they're defining some events for us. A is the student missed more than 2 days. B is the student missed between 2 and 4 days inclusive. C is that the student missed no days at all. And D is the student missed at least 5 days. The first thing they want us to do is list the possibilities of each of the events. And whether there's a question that asks you to do that or not, when events are numerical in nature, I think it is a good idea to list out the possibilities if there's not too many of them. So for event A, the student missed more than 2 days. So that would not include the 2, it would have to be more than 2, but that would be 3 or 4 or 5 or 6 or 7. And you could say actually that would go on to 8, 9, 10, 11, and so on, but in terms of what's possible in this chart, because we are randomly selecting one of these students, there isn't anyone who missed 8 days or more. So event A would just be 3, 4, 5, 6, and 7. And then event B is the student missed between 2 and 4 days, and the only number of absences between 2 and 4 would be 3 days missed, but it does say inclusive, so we're going to include the endpoints as well, and that would be 2, 3, or 4 days missed. And then continuing on, event C, the student missed no days, so that would be 0 absences. And event D, the student missed at least 5 days. Sometimes we get a little mixed up there because at least sounds like a less than, but really at least is that number or higher. So that would be 5 and up, which would be 5, 6, and 7. Again, just if you're a little confused by that, you're expecting it to go the other way, think about this. You need to be at least 18 years old to vote. So 18 or higher, not 18 and younger. So at least is language that is inclusive, includes the starting point, and then goes upward. And again, I would suggest doing this, even if there was no part to do it, I would just do it off on the side here, because you're going to see as we continue on that having those numbers listed out makes the rest of these questions a little easier to answer. Alright, so let's look at this idea of mutually exclusive. We saw the definition, but let's see it played out in the example. List all the mutually exclusive groups of events. So it says groups, so that could be any size. It could be a pair, a triple, or even a quadruple. So let's do that in order. Let's look for pairs that are mutually exclusive. Remember, that means that there's no overlap to them. So when I look at A and B, I see some overlapping possibilities, 3 and 4. Where there's overlap, there's not mutually exclusion, or they're not mutually exclusive. So these two are not mutually exclusive. When I look at A and C, I do not see any overlap, and so that's the characteristic you want for it to be mutually exclusive pair. So that pair is mutually exclusive. When I look at A and D, I see the 5, 6, 7 match up. So where there's overlap, that's a no to are they mutually exclusive. So I looked at A with everything. Now I'm going to move on to B. No need to go backwards, I already did that pair. But B with C, I don't see anything in common there. So I'll list that. And B with D, I don't see anything in common there either, so that's going to be another mutually exclusive pair. And then that's it with B. Then I'll check C with D. I don't see anything in common there, so that means those are mutually exclusive. And those are all the pairs that I could get. And then I start thinking about triples. What if I took A, B, and C together? If there's overlap anywhere, I have to say no. And there's overlap here, so that's a no. How about A, B, and D? Now the A and the D have something in common, and the A and B have something in common, so that's a no. And then how about A, C, and D? A and D have something in common, so that's a no. So are there any triples where there's no overlap? I think if you start with the B and leave the A out, that's where the trouble is. You'll find a mutually exclusive triple. A, C, and D, I don't see anything in common anywhere between any two. So as a triple, B, C, D is a mutually exclusive triple. Now it's possible you could have a quadruple, but we know A overlaps with a bunch of stuff, so there's no way that we can list all 4 of them and say it's mutually exclusive. And again, I would much rather look at these numbers to see if they have anything in common than to have to keep rereading the sentences to figure that out, so having listed this out is definitely useful for us. And it's going to continue to be useful as we start doing some probability questions. So find the probability of A and B, the probability of A or B, and then some triple ORs we'll look at as well. So first, for the probability of A and B, remember that that is overlap. So I'm going to write probability, and I'm going to try and look at the sets and think, well, what is the overlap of A and B? What do they have in common? And what I see in common between A and B is the 3 and the 4, the 3 and the 4. So what A and B have in common would be 3 absences or 4 absences. And remember, and means overlap, or what they have in common. And then when you do the probability, this is where it gets a little tricky. Sometimes people might want to make their numerator 2 here because I have 2 things listed, or 7 because 3 and 4 add up to 7. But when you go to do probability, if you're at all confused about what numbers to use, go look at what you're going to randomly select. And it says consider selecting a student at random. So when we do this probability here and all the rest of them, since it's student that's being selected at random, it's students that are being counted. And if you're counting students, then in the denominator you want the grand total number of students. And if I can pull this down here for a second, it says that there were 63 students in this class. So the denominator would be the 63 total that are in the chart. And then when I think about, okay, so how many am I going to count? I want to count students in the top. I'm not going to add the 3 and the 4 because that's 3 days missed and 4 days missed. So the 3 and the 4 are right here. But what I want to count is how many times did they show up, and that would be this bottom part. So there were 4 students who missed 3 days, and there were 5 students who missed 4 days. So when I do the probability, I want to count the 4 who missed the 3 days and also the 5 who missed 4 days, because any of those students would fall into the overlap. And then I'll change that to a decimal in a bit. For now, I'm just going to stop there and move on to part D. So when you go to do the OR, remember that instead of doing overlap with an OR, it's count all of the first one and anything that's new from the second. So for A, if I count everything in A, that would be 3, 4, 5, 6, and 7 days missed. And then I would go to B and say, is there anything new from B that I don't have yet? We can see from our underlining we already have the 3 and 4, but the thing that would be new would be a 2. So for this OR, I want to count any student who missed 3, 4, 5, 6, 7, or even 2 days. And if we went and looked at that up on the chart, I could say, let's see, if it's really 2, 3, 4, 5, 6, or 7, so we want to count all of these students. Now, when we do the probability on that, we still have to remember our denominator is based on the number of students total, which is 63, and the numerator would be any of the students in this box, and the students are listed by the frequency, so it'd be 10 plus 4 plus 5 plus 3 plus 3 plus 1. And you could add all that up. But personally, what I would do is instead of adding all those up, I would count the ones I don't want. I know there's 63 students altogether in that chart, but I don't want these 22 and I don't want those 15. So instead of adding up these 6 categories, personally I would prefer to subtract out the number of students that were in the 2 categories I didn't want. And either one of those, adding up the 6 or subtracting out the 2 from the total, should give you your probability. Let's go ahead and calculate those 2 decimals and fill them in. Remember, parentheses around addition or subtraction. So 4 plus 5 out of 63 is our first probability. So that one is going to be 0.1429. And then on the other side over here, parentheses when there's subtraction, so 63 minus 22 and minus 15, the total minus the stuff we don't want, divided by 63, gives 0.4127. And again, you would have been perfectly okay to go ahead and add the 6 you wanted instead of subtracting the 2 you don't from 63. Both ways work fine. In fact, just show you that real quick. 10 plus 4 plus 5 plus 3 plus 3 plus 1 over 63, same exact answer. So it doesn't even really take that much longer, but I think it's a good habit to get in, that if you were going to count more than half of your boxes, that you subtract the ones you don't want instead. You'll find that in the long run that saves you time. So when we move on and we start doing a triple OR, it's really not much harder. Let me just come up here and show you the Venn diagram idea on that. if they said you want A or B or C, and they had 3 circles there, then when I went to shade that in, I would shade all of the first one, whatever was new from the second one, and then whatever was new from the third. And notice that wording is essentially just like what we had before. It's just every time I go to the next event, I don't count everything in that event, I only count the part of it that's new. As long as you remember that part, just add in the new stuff. I think these ORs, you won't care if there's 2, 3, 4, 5 things listed. It won't be much harder as they add extra events. So when I go to do this one, they start off with A, so I would list everything that's in A, missing 3 days, 4 days, 5 days, 6 days, 7 days. Anything new from B? Yeah, we pick up the 2 then. And then is there anything new from D? Well, actually, no, there's not, because 5, 6, 7, those are things we have already. So it actually turns out that the way this was arranged, by the time we got A and B, we already had all of D, so there was nothing new. And that means our answer here is still going to be the same 0.4127 that we had before. So not only was that triple OR not any harder, it was actually kind of faster because we just ended up copying our answer from back over there. Let's go ahead and look at another one that will come out a little differently than that. Again, a triple OR, so I'm going to follow that same strategy. Count everything that's in B, and the stuff in B is 2, 3, or 4 days missed. And then add in anything that's new from C. C is 0 days missed, so that's new. And then when you get to D, you want to add in anything new from there, which is 5, 6, 7. All of that's new. So I'm going to add all of those things in. And there's what I want. Any student who missed 2 days, 3 days, 4 days, 0 days, 5 days, 6 days, 7 days. So you could add all those up, but if you look at that list, the only number of absences from our chart that is not represented here is 1 day missed. So I'm going to use the subtraction method here and say of the 63 students, I want all 63 of them except for the ones that aren't listed here, which would be students who missed 1 day, and there was 15 of those. So it's going to be 63 minus 15. And then go into the decimal on that one as well to finish it off. 63 minus 15 divided by 63 is 0.7619. And then just a quick comment there. Some students will find that this one was easier than that one, and they'll say that because there was no overlap. Remember, B, C, D was our triple that had no overlap in it, and that meant every time we went to a new letter, we got something new. So the reason people like that is because there's no worry about double counting. If everything that you come to is all new stuff, then you just count all of B, all of C, all of D, and you don't have to worry about double or triple counting stuff because there's no overlap. Here, if you did all of A, all of B, all of D, you would have counted, when you did A and B, you would have counted the 3 and 4 twice. When you threw in the D and counted 5, 6, 7, that would be double counting it because you already had it in A. So I don't find either of these to be more difficult than the other as long as you follow this strategy. All of the first, only the new stuff from the second, only the new stuff from the third. That is a method that will automatically avoid double counting, so it's definitely the method I would suggest to you. But there is a rule that deals with this case over here that says, look, if everything's mutually exclusive, it's actually a little bit easier to do in the sense that there's less risk of things going wrong, less risk of double counting because there's nothing to double count. So our special addition rule says if you have 2 events and they're mutually exclusive of one another, and then you're asked to do the probability that A or B occurs, then you can just take the probability of A and do that by itself. You can take the probability of B and do that by itself, and then you could just add those 2 together. And typically you wouldn't want to do that because you'd think, uh-oh, I'm going to double count stuff, but you would only double count the stuff in the overlap, and if they're mutually exclusive, there is no overlap. So that rule is special because it only applies to mutually exclusive events. And then that that rule can be extended. If you have a whole bunch of events and they're all mutually exclusive, then if you're asked the probability of the first one or the second or the third all the way through the list with an OR, then you can just keep adding them one at a time. Again, that's very special. You can only do that if they're mutually exclusive events. Otherwise, you would have to be very careful not to ever count anything for a second time. But if they're all mutually exclusive, just all of the first, all of the second, all of the third, no double counting will happen because mutually exclusive means there's no overlap. On the previous page, we ended up with the special addition rule, which the extended version said if you had several events that were all mutually exclusive, then if you were asked to do an OR question for those, you could just add all the individual probabilities. If you think about that, that might seem a little strange. Like you'd think if I had a bunch of events, then probably there'd be some overlap there. It would be kind of strange for there to be no overlap at all. And one of the ways I like to visualize this is imagine that you took like 50 hula hoops around your arm and you just flung them into a room. Would any of the hula hoops overlap, or would they all kind of land non-overlapping in a mutually exclusive way? I would think probability-wise there would probably be some overlap there. So you might think it would be strange to have several events that were mutually exclusive, but that can happen and does happen. It doesn't happen randomly typically. It happens because you have a sample space and you kind of purposely split that up into regions that make up the whole space that have no overlap, and you label each of those spaces as an event. And one of the ways that is really common for that to happen is if you take the classes from a group data table and you make each of those classes an event, then you're doing something like this. Because the classes make up everything that's possible, and one of the rules for making classes is there should be no overlap, and so we have no overlap among these 6 events. So let's look at what this problem's about and how the fact that these events don't overlap is useful to us. So a relative frequency distribution for all U.S. partnerships by receipts received from sales and services is as follows. And we've got our receipts that the partnership made under $25,000, between $25,000 and almost $50,000, $50,000 to almost $100,000, $100,000 to almost $500,000, $500,000 to almost $1 million, and $1 million and more. And then they have the relative frequency for each one of those events. And they want to know if we randomly select a U.S. partnership, then find the probability that the partnership obtained had receipts of, and the first one is under $100,000. So the first thing I'm going to do is just try and write out the notation for that. If it's under 100,000, then what letters is that? So let's see, under 100,000 would be from here up, and that would be A, B, C. So I'll write those down. But then when you think about, all right, it's A, B, C, is it A and B and C, or is it A or B or C? And to think about that, what you want to think is, do I have to be in all 3 of these at once to be under 100,000, or as long as I'm in at least one of them, will that be under 100,000? And it's impossible to be in all 3, but it's not impossible to be under 100,000. And if you're in any one of these 3 groups, you would be under 100,000. So since you don't have to be in all, just at least one to meet this description, I would say that this is an OR question. So A or B or C. But as we mentioned before, this A, B, C, there's no overlap because they're classes that had no overlap. And so according to the special addition rule, you can just take the probability of A, add the probability of B, and add the probability of C. And now we get to a little bit of a tricky spot, which is where do we find those? If they say we're going to randomly select a U.S. partnership, then we should want to count the total number of partnerships and then divide by the number of partnerships under 100,000. But there's nowhere in this problem where they told us how many partnerships there are total, so it seems like we're stuck. But if you look at the wording, it says this is for all U.S. partnerships, so I would say we're looking at population data here. So when they call this column the relative frequency, that would be the population relative frequency. And if you think about how did they get that, they counted how many businesses or partnerships had receipts of under 25,000, and they divided by the total number of partnerships. That's how you get relative frequency. And that's exactly the calculation we would like to make for probability. So we don't have the numbers to do it ourselves, but if you're given population relative frequency, then that numerically is the same as the value of the probability. So I can just fill these in from off the chart. The probability of A is the same as the population relative frequency for A, which is 0.601. And probability for B is the same as the population relative frequency for B, so that's 0.081. And the probability of C can be taken from the relative frequency as well, and that would be 0.88. And then if you add those together, you're going to come up with your probability for the overall event of being under 100,000. So let's see, that was 0.601 plus 0.081 plus 0.088, and that adds up to 0.77. But because I was adding 3-digit numbers, I'm going to write a 3-digit number. If it shows you just 2, it just means the last digit must have been a 0, and the calculator, selfishly trying to save its batteries, is not doing the 0. But if we know that it was supposed to be 3 decimals and they don't show it, it must have been a 0. Moving on to part B, we're going to keep using the same idea to continue on with these. So at least 500,000 is the next thing they want the probability of. So at least 500,000 would be from 500,000 and up. So that would be 500,000 and to a million in the million and more category, or events E or F. And just like we talked about in the last one, you don't have to be in both of those to be at least 500,000, just at least one, so that would be an OR. And then also, just like last time, you can just add the individual probabilities. And remember, we can only do that because they're mutually exclusive, no overlap. If that wasn't true, we'd be worried about double counting, but here that's not going to happen because there's no overlap to the events. And use those population relative frequencies as numerical values for your probabilities. So I fill in these relative frequencies in the probability slots, and then I add them together. And it looks like that's going to be 0.077. So that's the way that goes. If you have a bunch of mutually exclusive events, then you can add the individual pieces together without fear of double counting when you're going to get your probability answers for OR questions. And now we just show you a couple other scenarios that use the same idea but just have a special little twist to them that I want to make sure we discuss together. The probability of under $1 million would be the probability of, and let's see, under $1 million would be $1 million or less. So that would be going this way. Event-wise, that's A, B, C, D, and E. And I'll list that out. It's A or B or C or D or E. And there would be nothing wrong with going ahead and adding those probabilities together, this plus this plus this plus this plus that, and that would be your answer. But another thing you could do is say, well, wait a minute, these things make up the total sample space, and they add up to 1. So if I need to add these 5, that would be fine, but another option would be to just subtract out this 0.041, which is the probability of this event F over here. So I could say, since these all add up to 1, I could add the 5 I want, or I could subtract the 1 that I don't want away from 1, and that should also give me the same answer, and it would be a little bit faster. So the probability of F, looking at the relative frequencies, would be 0.041, and doing that subtraction, we get 0.959. So we could have done it by adding the 5, and that wouldn't take very long. But again, I've mentioned this before, if you're going to add up more than half of the possibilities, it's probably a good idea to subtract instead. And we're going to really see that kind of thinking pay off when we get to the last section of Chapter 5. So if you can make that a habit now, you'll appreciate it later. So let's look at one more version like that, 50,000 or greater. I'm getting a little bit messy here on the colors, but 50,000 or greater would be the split is here, and we'd want to go this way. So that would be C, D, E, or F would all fall into that 50,000 or greater description. So I'll write that notation down, C or D or E or F. And there's just 4 of them, so you could add those 4 probabilities together and it'd be no problem. But just like above, you could also say, you know, the ones I don't want are the A and B. And these things total up to 1. So if I take 1 and subtract the ones I don't want, that should give me the answer as well. And if I did that, that would be 1 minus 0.601 and minus 0.081, these being the relative frequencies from A and B rows up above. Now let me go ahead and put that in the calculator. So 1 minus 0.601 and also minus the 0.081 gives me 0.318. And I just want you to notice that if I went with the other option of, instead of subtracting these 2 from 1, adding these 4 that I wanted directly, that should give me the same answer. and it does. So adding those 4 is not bad, subtracting those 2 is not bad, but getting ready for later sections in Chapter 5, if we get in the habit of when we're going to add more than half the options, subtracting the others from the total instead, that'll save us a little bit of time. It saves us a tiny bit here, it'll save us more than that in those later sections. That idea of subtracting what you don't want instead of adding what you do comes from the complement rule. The complement rule says, let me show you a picture here. Let's say we were doing the probability of an event E or its complement, not E. If you were to shade that, you could say, all right, here's event E. Let's say that was the inside. I'll shade that in blue. And then the event not E is everything that's in that box but not in that circle, so that would be all this other part. And if you look at what's shaded when I'm done with that, it's everything. So the probability of an event occurring or not occurring would be 1. But then they're mutually exclusive as well. So you could say the probability of the two things separately could be added together, and that would still be equal to 1. And the complement rule just takes advantage of that, and it says if you want the probability of some event, you can get that by doing 1 minus the probability that it does not happen. And that's just algebraically moving this to the other side by subtracting it from both sides. So here's our complement rule. If you want to know the probability of something happening, you can work it out directly, but you could also figure out the probability that it doesn't happen and just subtract that away from the total probability of 1, and that'll get you there as well. So again, that's known as the complement rule, and I think that you should use that anytime you would have otherwise been adding up more than half of the possibilities. So when I had situations where I was going to add 4 things, or I could subtract 2, that's more than half, so I'll subtract the 2. If I was going to add 5, why not just subtract 1? That'll be a little bit faster. So the complement rule typically doesn't have to be used, but it can save us time. A little bit of time here, a lot of time in section 5.5, so and beyond. So we want to be able to use that whenever it's possible. We want to have that as a tool, and if we practice it here, it'll be natural to use it later. Okay, continuing on with section 5.2, we looked at the special addition rule already, and now I want to go ahead and look at the general addition rule and show what happens if we don't know whether or not our two events A and B are mutually exclusive. So let's go ahead and draw a Venn diagram of this situation and kind of think this through. So suppose we have an event A and an event B. Maybe they overlap, maybe they don't, so I'll show the possibility at least that they do. And then suppose we came along and we counted everything in A, and then we counted everything that was in B, which is what we'd do if they were mutually exclusive. Then a mistake happens, and the mistake that happens is we end up counting this overlapping piece 2 times. Now with an OR, we do want the overlap, but we don't want to count it twice. So what we want to do with this rule is say, okay, if you count everything in A and count everything in B, you're going to get the overlap twice. So what we need to do is subtract out the extra copy. So we're going to add the probability of A and the probability of B, but then we're going to subtract out the probability of A and B, which represents that overlapping piece, and it gets rid of the extra 1 copy that we have. So that's what the general addition rule says. Let me go ahead and show you an example of how it can be used to verify that it works. So consider rolling 2 dice. Let's find the probability of rolling doubles or getting a sum that is 6, and we're going to do that in 2 ways. One, by just using counting techniques that we had come up with previously and thinking about what the definition of an OR is, not the rule, but just the definition, and try and work it out that way. And then we'll try this new rule, the general addition rule, and see if we get the same answer or not. When I'm looking at this experiment of rolling 2 dice, it's always a little easier to work that out if I can make a chart and list all the possibilities. So I'm going to start off doing that. And not that we need to think about the 2 separate dice that much on this one, but I'm going to go ahead and show those as separate colors so we can imagine that we have one die that's teal and another die that's purple. And then we're going to look at all the different sums that you could get when you combine these together. So the 1 with the 1 is a 2, and so on. Let me fill this in quickly just using a pattern. So just a quick reminder, I did fill that in just now using a pattern, but the reason this is a 9 isn't just because it's after 8 and before 10, it's because it was a 6 on the purple die and a 3 on the teal die, and 6 plus 3 is 9. And in fact, whenever you do fill in a chart using a pattern like I just did to make it go faster, you should go and grab one and just double check that it is really matching the rule as well, which is the addition of the two numbers. Alright, now let's try and find the probability of getting doubles, or the sum is a 6. And doubles, just a quick definition on that, means that the two dice that were rolled are the same. So I'm going to go through and I'm going to put a circle around all the ones that are doubles. So this 2 is a double, not because it's the number 2, but because it was a 1 rolled with a 1. So if we roll a 2 with a 2, that would also be doubles. A 3 with a 3 is double 3s. Here's double 4s, double 5s, and double 6s. Notice not every 6 is doubles. This 6 is a 4 and a 2, so that is a 6, but it's not doubles. And then we have all the doubles circled, but they do want us to actually count all the ones where the sum is a 6 as well. So I'm going to go through and I'm going to put a square around all the ones that have a sum that is 6. Notice this one gets a circle and a square because it's both doubles and has a sum as a 6. And then everything that has a circle or a square or both around it is something that I should be counting for this probability. So first of all, how many things are possible? If you look at all the blue combo sums that we have there, there's 36 of them. And then how many of them meet the description? So the technique that I showed you before, and I'll show it again on a Venn diagram, if you want to do an OR by simple counting, then when you have the two events A and B, you want to do all of the first one and then only the new stuff from the second one, being careful not to double count the overlap. So what I'm going to do is I'm going to count all of the things that were doubles. So that would be the circled numbers, 1, 2, 3, 4, 5, 6. And then I'm going to add in anything that has a sum of 6 that's new, which would be 1, 2, 3, 4. And I'm careful not to count this one because I already counted it when I did the doubles. So I have 6 things when I count all the doubles, and I have 4 new things when I take the sum of 6. And again, new things. This one wasn't new, it had been counted already. So that's 10 out of 36. And if I divide that on the calculator, 10 over 36 is 0.277 repeating. So that would be 0.2778 if I rounded it to 4 decimal places. So that's just using the definition of an OR and thinking about that Venn diagram concept, all of the first and whatever's new from the second. Now I want to try it again using this new rule. So when we do the rule, we're actually changing it from one probability question to 3 separate probability questions. So the first thing I'm going to do is write out those 3 questions. The probability of doubles where the sum is 6 would be equal to the probability of doubles plus the probability the sum is 6, and then we'd need to subtract out the probability of getting doubles and the sum is 6. And when you do this, you just treat it as 3 completely separate questions. So you say, what's the probability of doubles? Well, if I roll 2 dice, there's 36 possibilities. How many of them are doubles? 1, 2, 3, 4, 5, 6. And then you add in the probability that the sum is 6. And how many ways out of 36 are there to get a 6 for your sum? 1, 2, 3, 4, 5. Now there might be an objection right there saying I shouldn't count this one, but right now when I do this rule I'm just doing the probability that the sum is 6 all by itself, and there's definitely 5 ways for that to happen. I'm not worried at this point about double counting or anything like that. I'm just saying how many ways altogether in that chart are there to get a sum of 6. And then the formula is going to correct for the double counting for us by subtracting out a copy of the overlap. So we're going to subtract the probability of getting doubles and the sum is 36. Remember that and is the overlap, so we've got our circled doubles and our boxed 6s, and this one is both, so there's 1 out of the 36 that met both conditions and is in the overlap. So that gives me 6 plus 5 minus 1, which is 10 out of 36, which is the same answer that I got above. So what I hope you would see out of this is that even though this new rule works, because it does match the answer we got the other way, is that we're actually better off just thinking about all of the first and whatever's new from the second, in the sense that we just had to do one probability that way, one fraction, instead of three separate ones that we combined together. And so that's my note here, is that it's usually easier to count rather than to use probability rules. So use the rules when you don't have enough information to solve by simple counting. So we have a little bit of an odd situation in that I just gave you a new rule, the general addition rule, and then essentially told you it's best not to use it, that it's better just to think your way through with the definition of an OR. And I do believe that that's true when you have the entire sample space laid out in front of you, and it's easy to see what the overlaps are and just avoid double counting them. But there are situations where the rule is handy. A lot of them are more theoretical mathematics situations. And one that falls into that is just kind of what I would call an alphabet problem, where we don't even know what our events stand for, but somebody's told us some probabilities and asking us to find another one. So let me show you how to use the rule for this example. The probability of A is given to be 0.4. The probability of B is 0.7. The probability of A and B is 0.3, and they want us to find the probability of A or B. So I'd like to do this by just simple counting, but to do that I'd have to know how many things are in the sample space, and I'd have to see the sample space. And I don't know, when there's a probability in there like 0.7, maybe that's 7 out of 10, maybe that's 70 out of 100, maybe that's 7,000 out of 10,000, I don't know. So it's hard for me to draw out that sample space and work it out that way, but I can still use the rule up above, which I'm just going to rewrite right here. If I want the probability of A or B, the rule at the top of the page says I can take the probability of A, add in the probability of B, and subtract out the probability of the overlap A and B. And all three of those things were given to me here, so I'm just going to start plugging them in. The probability of A was 0.4. The probability of B was 0.7, minus the probability of the overlap, which is 0.3. If I add these two together, I get 1.1, subtract out the 0.3, and I get 0.8. So kind of an interesting situation, especially if you're a math person. We don't know what our experiment is. We don't know if we're drawing cards, pulling marbles out of a jar, rolling dice. And we don't know what A stands for, B stands for, but yet we can still tell people the probability that at least one of those two things happen will be 80% just by using the formula. Let me just show you another variation on that real quick to wrap this up. Probability of C is 1/3, the probability of C or D is 1/2, and the probability of C and D is 1/10. Determine the probability of D. So the first thing that I want to point out, that hopefully is obvious, is that when you have a formula and it's written in terms of A's and B's, that doesn't mean that you have to have A's and B's in your problem to use it. So those are just placeholders. So the probability of any event or another event is the probability of the first plus the probability of the second minus the probability of the overlap. So that's true regardless of the letters. So I'm going to start out here by just rewriting the formula and writing it in terms of these letters. So the probability of C or D should be equal to the probability of C plus the probability of D minus the probability of C and D. So that's just the same formula, just written with the new letters. And then I'm going to start plugging things in. And this time we were given different pieces. The probability of C or D this time was given to us as 1/2. And then we have the equal sign, and then the probability of C was also given, that's 1/3. And then it's plus the probability of D, and that's not given. In fact, that's the thing we're trying to find. So I'm just going to leave that in there as an unknown. You could put an X as a variable for that if you want, but I'm just going to write P of D. And then the next and last piece is minus the probability of C and D, and that was also given to us as 1/10. So you can use this formula to find any of its pieces. I would argue it's designed to find an OR, and it makes the most sense to explain in terms of the OR being by itself. But if you know a formula and you know algebra, then you can find for any of these pieces provided you know all but one of them. And so what I would want to do here is a little bit of algebra to rearrange. To get this P of D by itself, I could subtract 1/3 from both sides. That would cause these to cancel. I could add 1/10 to both sides to cancel these out. And then what would I have? I have this P of D would now be by itself. And then on the other side I had the half that was already there. I had the 1/10 that I just brought over is now positive, and the 1/3 that I brought over is now negative. And then what do you need to add and subtract all three of those fractions? Gave a little pause there for you to think about it, and it's very common for what people would say is a common denominator. And if you want to do all the common denominator work, looks like it would be maybe 30 for the common denominator, be my guess. But actually, you don't need to. You could just use the calculator and just enter each of those fractions in, and then just press enter to get the answer. So 1/2 plus 1/10 minus 1/3, just using the division for all the fractions, and I get probability of D is 0.2667. So it's not a fraction answer, but we give decimal answers all the time in stat, so it's an approximation. If you needed the exact answer, you'd do the common denominator, but we're always good with a decimal, so I just went ahead and went straight to the calculator. I would caution you on that, though. I went to the calculator after I did the algebra. Sometimes people put decimals in all these spots. That's actually a lot messier. Plus, you might round in several places, and the rounding error could build up, and you could end up off in your last digit. So go ahead and use the calculator, but do it as the very last step. All right, and then the final question on this, are events C and D mutually exclusive? Explain. Well, recall that events are mutually exclusive if the overlap does not exist, or if it's impossible to land in both events at once. So the way you can look at that is just look at the probability of C and D, and if that's 0, that would tell you that it's impossible for those to occur at the same time. If it's anything other than 0, it means that it's possible for them to occur simultaneously. So I don't know what event C is, I don't know what event D is, I don't even know what experiment we're doing, but according to this, 1/10 of the time C and D happen simultaneously, so it's certainly not impossible for them to overlap. So are they mutually exclusive? No. Why not? Because the probability of C and D is equal to 1/10, not equal to 0. If you recall the definition of mutually exclusive events, if they're mutually exclusive, the probability of C and D would be equal to 0. So since we got anything other than that, we know that these two events are not mutually exclusive.